In this video, I'll show how to fit a wide range of models using BugsXLA. In this first example, we have a small experiment with the response is binomial in nature. As you can see, this has already been populated. The distribution is binomial. As you can see, this is the list that's available in BugsXLA. And with the binomial, you have a choice of link functions, and here we have chosen the logit. For a binomial response, it's specified using this terminology, with the R being the number of successes and N being the number of units. Here we have a fixed and a random factor specified. If we want to add a second factor, we'd use the plus operator. If we wanted to also include the interaction between these two factors, we use the colon operator. A quicker way of doing that is to use the star or asterisk operator, and that will fit both the main effects and the interaction. And as you can see on the right hand side where we have the output for this example, that's what was chosen, and you've got the two main effects and the interaction displayed. Although not appropriate for this model, if you actually wanted to fit root as a factor nested within seed, you use the / operator. And this, in effect, fits the main effect of seed plus the seed by root interaction. In this second example, we have a response and two covariates, and we want to fit a second order polynomial in the two x covariates. So if we look down here how it's been specified, x1 star x2 will fit the main effects of the covariates plus their cross product term, and then here we've used brackets with their power to 2 operator on the end, so that will fit the squared terms for x1 and x2. So if you look across at the output, you can see how it's interpreted that model statement. In this third example, we have an experiment in which we want to fit quite a complex model, and we show how we can do that quite efficiently using a combination of brackets and the asterisk operator. So if you compare this statement here with the terms that are being fitted, you can see that this will fit the main effects of all of those 5 factors, but only a particular subset of their interactions. So in this case, you've got all the interactions between the x variates and all the p variates, plus you've got the interaction between x1 and x2 because that's explicitly specified at the end, but you have none of the interactions between the p variates here. In this example, we have data measured over a period of days on the weight of rats, and a growth model, a fairly simple growth model, is fitted. And this is specified as a random coefficient model, so that would be a linear with respect to day, but with the coefficients for the slope and the intercepts being able to change for each rat. By specifying it this way, BugsXLA will fit a multivariate normal distribution to the intercepts and the regression coefficients, and summarized as you see on the output on the right hand side. In this next example, this is similar to the previous, but here we're measuring the height of young children at various ages. In this model, we're fitting a longitudinal error structure, and more specifically, this is unstructured. And this is how you specify this in BugsXLA. More help on this is provided by the help feature here, which explains the different types which you can use. There's basically only the unstructured and the autoaggressive one option that can be used here. But as well as specifying the units, which in this case is subjects, you can also optionally specify a variable which tells that what the time is for each of the observations. When this is not specified, it assumes that they're in time order and the same time for each subject. In this example, we have a meta-analysis of clinical studies where the response is binomial in each case. Now, this could have been fitted using a binomial distribution, but here we use a normal approximation to the binomial by summarizing for every study the proportion of successes. We have a column which also quantifies the standard error associated with that proportion. And optionally, although it wouldn't really make much difference using it in this case, we have a approximate number of degrees of freedom associated with this standard error. And BugsXLA allows you to analyze summary stats data like this, which is typically it's used in this sort of case where you have meta-analysis data or summary data for a series of studies. And the way to do it is to specify, check this box here to say you've got data in this form, and then you, with a semicolon separated list the three columns. If you don't include the degrees of freedom column, which is optional, then it will assume that the standard error is a known value rather than an estimated value. In this final example, we have an experiment in which the response is ordered categorical. The response is in this column called clarity, which is a value from 1, 2, 3, or 4, which the patient has said how clear certain instructions were for a medical device they were using. If instead you have counts data for each of the 4 categories, which is here now got descriptions, easy, clear, not clear, and confusing, you can use the ordinal distribution and specify the response as a comma separated list